Hello community, so great that you are back. We have some brand new AI research published today. So, you remember DeepSeek's GRPO? Today we're gonna talk about DAPO and VAPO. Let's start. I give you the main results right away and you decide if you want to continue to watch the video. You remember with R1 GRPO, Group Relative Policy Optimization, we used here group-based reward normalization over multiple responses here by prompt and a symmetric clipping. And therefore we were able to stabilize here the reinforcement learning training without, and this was the beauty, an explicit value model. But of course, we encountered some problems, but this is where it all started with R1 DeepSeek. Today we're gonna talk about here a new development by ByteDance Seed, and they used here the next step in the evolution, now a value-free method, to focus here on the shortcoming here in the policy optimization through now an asymmetric clipping, some dynamic sampling, a token loss computation with additional term, and a very nuanced reward shaping. And they directly address here the issues here of an entropy maintenance and the long chain reasoning task, how we can improve here the gradient utilization, where we encountered problem with R1 GRPO. And then, just 3 weeks later, we have even the next step in the evolution here. Today we're gonna talk here about a new methodology that will incorporate again a value model. And we have 4 new items, and it will overcome the key limitations of value-based methods that we know from PPO. So, amazing things here, maybe the next components here of an R2. Let's have a look. Yeah, the performance. Just want to show you, this is what we're going to achieve. We have here, if we look here, a particular benchmark, AIM 2024, the accuracy you have here, and then simply the training step on the x-axis. And you see here, this is here the performance point, the performance data of R1 with GRPO that we know. So about 10,000 training step, and we had 47 in the accuracy. And now what we're gonna look today is we're gonna achieve here with half of the training steps, the same little bit better accuracy, and then with even less and again an increase in the performance. So if you can halve your training step, if you train R2, this is really something amazing because the costs go down, the time go down, the utilization here of all your computer infrastructure, you are so much more efficient. Isn't this beautiful? Let's have a deep dive. And I will show you how this video of today is connected here to my video from 2 days ago, where I showed you the latest development by DeepSeek itself about the latest generative reward model, and I show you how we can use both elements and how they fit together. So let's open up this video. Now, we had March 18, 2025, a beautiful publication here, ByteDance Seed, then Tsinghua University, University of Hong Kong, and Tsinghua Air and ByteDance Seed, about an open source LLM reinforcement learning system at scale. So they had now a decoupled clip and a dynamic sampling policy optimization. Let's have a look. We have a project base, you have the free GitHub, everything is available for you. As I showed you here, the first one is here, they said, hey, you know what, when we had now ByteDance, our initial GRPO run, we achieved only 30 points. So we were only about here in the performance data. And then they investigated and they developed here this DAPO. This has now the same performance like R1, but with half of the training step. If you want to know more, because this is here the DeepSeek R1 Zero model, I explain everything about Zero and whatever models we have here in this particular video for you. So then they developed DAPO, and this was developed here to address here the challenges they encountered in training here the large language models via the reinforcement learning for those long reasoning tasks. You know, this O1 model by OpenAI, this R1 model here by DeepSeek. And they looked especially how to improve the performance for test time compute scaling, TTS, or inference scaling. And just to remind you, if you're not familiar with GRPO was great, but we had still some little problems. No? this GRPO just suffered from issues as an entropy collapse, where the model quickly becomes overconfident in a very narrow set of outputs. It is limiting its exploration of possible reasoning path. And we had a gradient instability. In particular, when dealing here with long chain of thought responses and some sequence length that varied dramatically, we noticed that the gradient was not a stable gradient to deal with in those models. So they said, okay, let's introduce solutions. And they developed for DAPO here 4 new main techniques. So at first, you get it, instead of using here the symmetric clipping range here, they decoupled here the lower clip thresholds from the upper clip thresholds, and they have here now an asymmetry, and they can now ensure that the low probability, the exploration tokens, are now not overly suppressed, thereby maintaining here a diversity in the long reasoning. Then they simply filtered out prompts that produce here just trivial gradient signals. Beautiful solution. But then here, with the token level policy gradient loss here, they compute here the gradient loss here at the token level. And this was especially valuable if we have responses that have a very short answer in a logical chain, or you have a real long causal reasoning chain. And finally, they said, yes, we want also, because sometimes in a long reasoning chain, you have a wrong end result, but 50 or 60 or 70% of the causal reasoning chain was correct. Just at, let's say, 80%, some wrong step happened in the causal reasoning, and therefore now the result is wrong. But with a soft penalty for truncated responses, they were able to preserve here some useful partial reasoning up until now the model made a wrong turn. And those 4 elements, they discovered it and they implemented it. And I think this is great. This is really a spark of genius. And if you are, we go now to the next level here, see this here in a mathematical formulation, and it is so much easier than when I talk to you and explain it to you. This is here a PPO. So we have here the PPO updates here, the policy by maximizing this objective here. And what we need here, of course, we have a question and an answer pair from the data distribution D. We have an epsilon, is here the clipping range here of the importance sampling ratio. We have a hat, this is our estimator for the advantage at a particular time step t. And given here for PPO, remember from OpenAI 2017, the value function and the reward function R. And then you can use here the generalized advantage estimation here to calculate all those PPO parameters. And this was 2017, beautiful. Now with GRPO, remember R1 or mathematics here, and especially they said, okay, now GRPO eliminates now the value function and estimated the advantage in a group relative manner. So for a specific question answer pair, behavior policy, pi old samples here group of individual responses, and then they are normalized on a group level reward without here a value function and a value model. And this became so beautiful. Yes, of course, we could have here a Kullback Libel divergence penalty term, but this was easy, no? GRPO. Now with DAPO, we have now the decoupling clip and a dynamic sampling policy optimization. Guess what? We have now an asymmetry in our clipping. I explain what this is, what it will bring us in the performance. But just for an overview, this is now how the formula modify. Simple. And if you say, what is all this thing here? I have a specific video where I explain here each and every term to you. So you will see, understand here the policy model, the reward model here, the optimization in general. So a little bit of AI math. It is a little bit funny that it's not boring. Let's come to the core element here of my video. Now, VAPO evolves now from DAPO by incorporating now a value model. We looked at the 4 steps of DAPO, and now we add a value model. And you might say, why? Through a value pre-training, this was the new element here, a decoupled and length adaptive generalized advantage estimation plus some additional loss terms, we can now overcome the shortcomings of DAPO, and now we have VAPO. So we have a better performance, 10% jump, improved training efficiency, and an improved reliability. So nice. Let's have a look at this. Now, you might ask, hey, what is now here the Connex, no? Because 2 days ago I showed you here the latest reward model here, the generative reward model by DeepSeek, so where DeepSeek is going for the R2 model. How does this fit now here with ByteDance Seed with the VAPO? Is there a context? Well, of course there's a context. Remember this video where I showed you here the new DeepSeek RM? And remember, I told you about the inference run, but before we had here the training time. And I told you we have here the classical rejective fine-tuning and the rule-based reinforcement learning. And here, for example, DeepSeek utilized here GRPO. So if we are now in a position here, in the rule-based reinforcement learning of this training this new R2 model, we could theoretically, or DeepSeek would use now the technology from ByteDance. This would now really interesting. No? Remember, DeepSeek used here GRM with the original settings of GRPO. Now, if you want, we have now the next evolution of GRPO and even the next evolution after that. So it really looks interesting what here the R2 model is gonna be. I just want to tell you something. My subscriber now continuously asks me, hey, why you not present any AI research topic from OpenAI? They tell me, hey, you show us videos from MIT, from Harvard, from whatever, in cooperation with, I don't know, Tsinghua University or Hong Kong University or Singapore AI. Why you don't show us anything, the new AI research results from OpenAI? And I just can tell you, OpenAI doesn't publish any information currently. I receive nothing from OpenAI regarding any new technology, any new advantages that they have, any new methods they're developing. I would love to present you something from OpenAI. I pay now for, I don't know, 3-4 years every month for OpenAI, and I'm waiting that they publish some new research, I don't know. But unfortunately, with this new commercialization of OpenAI, I have nothing, I receive no information, I have nothing to present to you. All the cooperation between the American with MIT, Harvard, or wherever you are, UC Berkeley, UC Santa Barbara, with Chinese partner, they are all on open source objects and they are somehow connected to R1. Therefore, I can present you new research. I have nothing by OpenAI. OpenAI has no publication currently. So, okay, let's have a look now at this study of today. And this is here on our VAPO. So we have our value-based augmented proximal policy optimization. You say, yeah, there's the PPO. No, this is PPO, the old-fashioned PPO. Yeah, but they decided to go not with VAPPO, but they decided to go with VAPO. Beautiful, so I respect what they want, but you see, we're here at the 2017 OpenAI Proximal Policy Optimization, and now here our friends here in ByteDance here have developed here a much better value-based augmented PPO. And they implemented and the results are impressive. I can show you here, you've seen this. This was here the performance data from R1, and now with half of the training steps we had DAPO. And now let's talk about VAPO. Isn't this beautiful? I was just wondering, you see here this kind of periodicity. I was wondering if they would have trained it another 1000 training steps, how far the performance would have gone up. But okay, these are the data that we have. So again, 4 key advancements in VAPO. As I told you, VAPO pre-trains now the value network using a classical Monte Carlo return structure. If you want, you can regard this as a warm-up phase. What it does, it reduces here the initialization bias for our long chain of thought reasoning chains. And then instead of using here a single generalized advantage estimation parameter lambda that is valid here in the classical case for both, remember, the value updates and the policy updates. In VAPO, we have now those terms decoupled. And they use now for the value network, their lambda is set to a specific value to avoid here this bias. And for the policy network, they use here a lower lambda. So not only that, we have here from the clipping an asymmetry, now also from the generalized advantage estimation between the value and the policy network, they also decouple this and we have here an asymmetry given because we want to achieve different things at different levels. Let me explain. With the value network now we have a lambda that is now fully propagated, the final reward without a decay to avoid the bias. This is what we want. I'll show you this in a minute. And the policy network uses here a lower element to improve here the convergence speed. Great. Then 3, given the response, it can vary now significantly in length. Remember our chain of thought augmentation path? Now VAPO adapts here a parameter dynamically adjusting for the sequence length. And a hyperparameter, so you have to play a little bit around with alpha to have a better balance bias and variance across short and long responses. Because there is a performance difference if you have a long answer and a very short answer. You don't need a long answer. The shorter it is, the better. But you have to take care. And they build here, if you want, a length adaptive generative attention estimation. Plus, they have here now a group sampling technique that we already know. And they add here some positive examples, loss elements here to the loss function. So they want to, if you want, focus more on the positive examples, on the valid examples. And this is it. Let's make a short interrupt here. And it's perfect position because we go now here from DAPO to VAPO. Why we have suddenly the value model? What is the value model doing here? We got rid of the value model with GRPO. Now it is back. Why? Well, it's estimating the expected return from each state, but with a much finer granularity. So if we, as I just showed you, the value network is now warmed up on a Monte Carlo estimation from a fixed policy before the policy updates will begin with, this gives us now a better starting position, a better initial condition and estimation during the policy optimization. Plus, if we separate our lambda parameter for the value updates and for the policy updates, we receive in general a better signal ratio. And I told you for the length adaptive, our discount factor lambda now is dynamically based here on the specific length of the generated sequence here of causal reasoning. And this is improving our performance. But now we have the time to look a little bit closer again on the value model. Why? You remember it gives us here the expected cumulative reward starting from a given state S, and this is what we need for a higher quality answer. Now, you remember with PPO we had an advantage function denoted as A hat, and it measured simply how much better a given action is compared to what was expected. And we calculated, look at my old videos, this with a temporal difference error, and this was the simple formula with the reward here and the gamma factor, the discount factor, and this was here the policy gradient updates in the variance reduction. Now, this value model has a particular kind of sensitivity. So for tasks requiring now our long reasoning chain, our chain of thought here, the sequence length can be highly variable. And bootstrapped value estimate, or whatever you have, can now become biased if our value model is not appropriately trained. This means we have, and they discovered this, with a warm-up phase. This warm-up phase, pre-trained now with the classical Monte Carlo returns, helps us to fix this bias. So this warm-up phase now reduces the bias associated with initialization here from a reward model. And then, as I showed you, decoupling now here particular parts for the value updates from the policy updates improves here further the performance. It gives us a better and faster convergence. And we do the same with a length-specific lambda parameter that we have a dynamic factor included now for the longer sequences. Also questions about clipping. Let's do the clipping here in a minute. You remember clipping? We discovered clipping here in the PPO. And the idea was simply to prevent the policy, the delta, the incremental policy optimization from changing too fast, too abruptly between our updates. We wanted to have a smooth transition here from one policy to another state. So for large unconstrained update, they can destabilize here our training, and therefore we invented clipping, if you want, to restrict here the update size, maintaining here the trust region around the old policy. And if you really remember here my very old videos I showed you, before OpenAI developed PPO, we had this trust region policy optimization. And PPO was built as, if you want, the next evolution of the trust region. So you see, everything is connected to anything else here in AI. Now, GRPO and the early PPO variants, we had a symmetric clipping because it was the easiest thing to calculate, to code. Yeah? So this means mechanism treats both the increases and the decreases in the token probability identically. But we encountered problems because we don't want this. You remember, we only have this sensitive balance here between we want to explore new areas here in the solution space, but at the same time, think about Monte Carlo tree branching out. If we have a successful path, a successful branch, we want to go deeper and deeper until we reach the solution. So this equilibrium between exploration and exploitation of already good path, this is now coming in here. Problem one was when a token has a low probability in the old policy, its potential to be increased significantly was hampered, of course, by the upper clipping bound. So this limitation restricted here the ability of the model to explore alternative reasoning path. But this is essential. We want to have a self-learning, a self-reflective AI model for the long reasoning change. So this was a problem. Problem two that we encounter was the entropy of the output distribution. It collapsed simply. This was not good at all. So ultimately reduces here the overall exploration capacity and hinder our discovering of improved reasoning path. So somehow we had to get rid of the symmetric clipping, and guess what was the solution? An asymmetry. So you see, rather easy to understand. If you look back at the last years and you understand all the different elements in the timeline, you see how one new methodology is built upon the other methodology. Let's come to an end. And I wanted to give you here a summary. And an AI helped me here to summarize this in a beautiful table. And here you have it. GRPO, DIPO, and VAPO. I also do this for myself because you're not going to believe it. I go back to my own videos if I want to have this, one view on everything that is in this video. So this is it also for me. And I have here the overall approach. What is it? A value-free reinforcement learning with group-level reward normalization, value-free reward learning, reinforcement learning enhanced for exploration via asymmetric clipping and dynamic sampling, and value model none, and yes, advantage, clipping strategy, loss function, reward shaping, stability. This is it. Now, I know me, I always want to go to the next detail step, so one level deeper. So if you're interested, I have also the details, but maybe this is only for me, maybe you are not interested. But anyway, I have here now a little more detailed analysis. You see the value model, what is here the value function here, what is happening here, how we do here the decoupling here of the generalized advantage estimation, the decoupling, the different length adaptive. This is, if you're interested, the clipping strategy now in much more detail, the sampling strategy compared here between the three models, the loss calculation, the reward shaping here, and finally the performance. And you see here with the classical one, we were here about R1 level. Now we reach here 50%, and we are here at 60+% of AIM 2024 benchmark accuracy. Okay, I think this is it. Try here this new element of a summary here on just one view that you see here, everything that we talked about. I hope you enjoyed it, and I can tell you this development just took 3 weeks, and we have a performance jump here from 50% of 60%. And if this continues, my goodness, I'm really looking forward to the R2 model. If you enjoyed it, if you found some new information, hey, why not subscribe? And I see you in my next video.